Welcome, everyone. Today we have Professor Alessandra Di Pierro talking to us about quantum kernels, challenges and solutions. While we eagerly look forward to her talk, let me tell you a little bit about her biography. Alessandra Di Pierro has been an associate professor in the Department of Computer Science, University of Verona in Italy since January 2011. Before then, she was a researcher in the Department of Computer Science at the University of Pisa, Italy. She also received her PhD in computer science there. Alessandra's research interests are in theoretical computer science, with a main focus on the theory of quantum computation and its applications to machine learning. She is the principal investigator of the QUI Lab, Quantum Information Laboratory, research group in the department. Since 2017, she has been both a member of the steering and organizing committee of the annual QTML, Quantum Techniques in Machine Learning Conference, and field editor for quantum software for Springer journal Quantum Machine Intelligence. Alessandra, we look forward to hearing your talk.
Thank you very much for your introduction. So yes, I will tell you about quantum kernel today, but before then, I thought before introducing the quantum stuff, I would like to give some picture of the classical the classical theory and the classical algorithm in machine learning, in supervised machine learning. So first of all, machine learning is really a big field, and this picture gives an idea. And today I will only concentrate on a very small part and a small part of the small, the small ball, which is supervised learning. So supervised learning, you know, I don't know how many of you already know the classical machine learning or algorithm of supervised learning, but just to be on the same page, I will introduce the basic notions of what supervised learning problem is. So, and the problem is that we have basically some data set and some training data of which we know we associate some labels. We know something about this data. And these labels are in output domain Y. So we call X, Y these training pairs. So is the information which, from which we want to learn to guess or predict some new unclassified input, some new input data will be classified according to the labels in the output domain. By using this algorithm or learning algorithm or classifier that is based on the training data, the information that we already know. So two very popular methods of supervised learning are linear regression and classification. Linear regression is essentially what we use for predicting, forecasting, and finding relations between quantitative data. And classification is applied, is a similar method, but applied to discrete data set. So this is the picture. We have, as I said, the training set, some training data with already labeled attached to them. And then we have this learning algorithm that uses this training set to formulate a hypothesis or model which can classify or can predict what the label Y is for a given unknown data X. So typically, Y is a continuous variable for regression problem, and it is a discrete variable for classification. So please interrupt me at any point. I'm just, I mean, if I'm saying something that you already know, just stop me. Otherwise, please ask questions. So just to be, to give an idea of what a model is, a learning model is, so we can say that the model essentially define a relationship between input data and prediction, the so-called labels, and basically is a function. If we want to look at it as a from the mathematical point of view, or we can look at it as an algorithm computationally. The model can be deterministic or a probabilistic model. A deterministic model is essentially a function which basically takes some input and associate some output y, the labels, to that input based on some parameters. These are called base weight vectors and are used for optimization purposes, we'll see later. And a probabilistic model, instead of a function, actually tries to learn distribution over the data. A distribution of which gives the probability of y given given x, the data, and theta are again the optimization parameters, the weight. So both this model and the deterministic model are called, the one that I just presented are called some discriminator, discriminative model. Completely different is another probabilistic model, which is called the generative model, which instead is based on a joint probability of x and y. So you need to know at the same time the input and the label. So the generative model is a little bit more complex, but is also used for different and more complex problems, for very complex data, and also for unsupervised learning. Typical examples of generative models are, for example, the hidden Markov chains, or the GAN, the generative adversarial network. Okay, so I hope this this is to clarify. We will talk about the deterministic model essentially. So we'll concentrate on discriminative model. And for this model, basically the central notion is the notion of a kernel. Because our objective is, given a set of empirical data, is to, the objective of the learning procedure or the model is to generalize this information in order to classify an unknown data in a similar way as the training example. Therefore, for this, we use a similarity function. This is essentially a kernel function. The kernel function that is defined in terms of a feature map. The phi is a feature map, is a function mapping the input data into a space, in an inner product space, and the kernel is defined in terms of this inner product in the feature space. The idea, so this is just a very simple example. So if our data are simply the point in the plane, then we can define a kernel by using the feature map, mapping each vector, two-dimensional vector, in a three-dimensional vectors, like this, for example. And then the kernel of x and x prime will be the inner product between phi x and phi x prime, which is this, after very easy calculation, you will find this, which corresponds actually to the square of the inner product between x and x prime. This is a very simple example, and actually the kernel is the feature map is very easily computable now, but the idea of the kernel is to actually allows us to make a problem which is nonlinear, a nonlinear separation between data, to make it linear by going to by mapping the data into a space of a higher dimension. So for example, here we have, if our data are just points in a line, then our problem is to classify according to two labels in two classes, the red and the green. Then obviously we cannot do here a linear separation. We would need a non-linear separation to classify, to separate these two groups. But mapping the data into the plane, actually here we just need to add a dimension, which is the y dimension, which is x squared. Then you will see that in this way we can easily linearly separate the two classes, the green and the red point. So basically, a discriminative classifier is something that is a hyperplane that allows us to separate the two classes. Right? This is our objective, and this is what they and this is how we are going to solve our supervised learning problem, our classification problem. But the point is, what is the best separating hyperplane? Because in this picture you see this line, but actually any line, I mean, there are infinitely many lines that could be good, could separate the two classes as well. So the problem is to find the best one. And what is the best one? Well, we want to be very precise in the classification, and therefore we should avoid that, for example, the green point get too close to the separating hyperplane, because this would easily allow the kernel not to be enough to classify it correctly. In other words, we should define the separator in a way that is at the maximum distance between the closest point in both classes. So I will explain this better. Basically, the best hyperplane separator is the one that is obtained by maximizing this margin, right? And there are some, mathematics here, and you can see that we can define this margin as the inverse, actually, of the norm of W, where W is essentially defining the line. Okay, so this line is W TX plus this offset B, and the point on the line will be those satisfying this equation, and of course the red point will be those below, and therefore satisfy the equation of being equal to satisfying this equation. And the point, the green point will satisfy this equation where expressing that they are labeled with 1. Okay, so the problem is to define this optimal separator, this best optimal hyperplane, and this is a constraint optimization problem. Therefore, we have to minimize this expression. So W are the basically is defining the upper plane, and this is our objective function, so to say. And this will be subject, of course, to the fact that each training set, this xi that are the data we know and that are already associated to a label, satisfies that, okay, if xi is labeled -1, then of course must be less or equal 1. If xi is labeled with 1, then this equation, this constraint must be satisfied. I hope it's all clear up to now. I don't want to be long in the mathematical details, but this is a constraint optimization problems and can be solved very efficiently, typically by constructing the Lagrangian, which internalize the constraints. And so you get these Lagrangian multipliers. And therefore, what we have to solve is actually so our objective function becomes this one, where W is nothing else than alpha j, yj, xj, overall the training set. And that's the important thing, as you see now, our line is expressed in terms of basically the inner product of all the pairs of training set. So we actually don't need to know the value of each xi, xj, but we just need their inner product. Okay, this is important because then because of what is called the kernel trick. The examples that I shown you before are very simple, but the feature map, so going to another space, a higher dimensional space, could be very complicated and difficult to compute, costly. Okay, and
sorry, can you hear us?
Yeah, now I can hear.
Sorry to interrupt you. We had a question from the audience, and
I can see on the chat.
We had electronic problems to convey to you, but now we can ask. So, thank you.
Hi. I have a question for you. So you map the data into a higher dimensional space in order to be able to have a linear separatrix.
Correct.
So that's one criterion for your endeavor. But my question is, do you also want this higher dimensional space to be of as low dimensionality as possible?
At this stage, I think, no, it can be even infinite dimensional. Actually, that's why I'm introducing now what is called the kernel trick, because as you said, this feature space can be very complex, very high dimensional, and computing for each input data, its image in the feature space could be very costly. So there is no, it can be as complicated as you like, okay? But the point is that we don't need to compute explicitly this phi, so we can just refer implicitly to this feature space. as long as this mapping ensure what is called the is a positive, the kernel matrix that we get is a positive definite matrix. Okay, so when you compute all the pairwise inner product, then what you get is a positive and definite matrix. And this is because of the so-called the Mercer condition. There is a theorem, the Mercer theorem, that says that K is a valid kernel. And this means that phi exists. You don't need to explicitly define it, but you know that phi exists if the gram matrix, which is the matrix of all the inner product over a very possible pair of points in X, is a positive semi-definite matrix. So we know this theorem is I mean, it's very important to define kernels, because we don't need to refer the feature space that can be as complex as we want. Okay, as long as K is a positive definite semi-positive positive semi-definite matrix, then we are guaranteed that this feature space exists, and that the kernel is the inner product of in the feature space. Is that have I answered to your question?
Thank you for the answer. I have a question related to this kernel now. So this kernel is a scalar product of two vectors in Hilbert space.
Exactly.
So in general, it's non-symmetric and complex, right?
Yeah.
So
yes.
do you work with...
Well, it is a complex number. It is symmetric, right?
How do you know that it is symmetric?
No, you're right. No, in general, it is not. But for particular cases, it is. So you get a matrix which is upper triangular. But you're right. It is not. This is just a complex number. Okay. Yes. And the way we define the classifier is to use exactly the line that we have constructed, where instead of the inner product between xi and xj, the input data, then we basically compare the new data z with each training data, okay? And essentially, we assign the label based on a majority vote, essentially. So we will get a sign here depending on this similarity. So if the majority of xi gives a minus sign, then we will get a minus label, otherwise a plus label. Is that clear? So this is our classifier based on the kernel and the expression of the and our separators, okay? Where we have replaced this by our kernel, okay? So all we need to define our classifier is to know the kernel matrix, and the Mercer theorem says that we just need to define a semi-positive matrix, definite matrix, and this is enough. Is that clear? So we will concentrate on this notion of kernel, and essentially to define our discriminator, our classifier. And if this is clear, then I will go to the quantum part. Otherwise, if you have more questions, please ask.
I don't think there are questions. Thank you, Alessandra. You can please go ahead.
Okay. So this is just an example. You can see that this is a very widely used kernel. It's the Gaussian kernel. And this is a kernel, and you can show that this is the matrix that you get is semi-definite positive, and therefore you don't need to specify in which inner product space you actually are working, and of which space this is actually the inner product between X and X prime. Okay. Okay, now I just want to very quickly, I mean, this is there is some very complicated math behind that, but we can also have a least square formulation of our classifier that is typically called, the one based on kernel is typically called a support vector machine, right? And so instead of using constraint, we use equalities, okay, by just adding, introducing some error terms, this EI, okay, we transform every constraint into equalities. And by constructing again the Lagrangian, imposing this condition of optimality with the partial derivative and so on. So we get actually that all we need to do to define our alpha, our kernel is actually, and therefore our separating line is to solve this system of linear equation. This formulation is important because an important approach to an important quantum kernel is defined on this formulation of the support vector machine. Okay, it's called this. Okay, let's go now to quantum machine learning. Just a few historical, information. Machine learning actually was appeared into the theoretical computer science realm in the 80s, okay, with the work of Leslie Valiant on the probably approximate learning. At the same time, there were the first theoretical model of computational model for quantum computing, right? With the Deutsch, Benioff, Feynman, Manin. They started to introduce these theoretical models, computational model for based on quantum mechanics. Then today, we're actually already in the 1997, there was introduced a kind of quantum-based PAC learning, but in the 2000s we have, witnessed this new area which is called quantum machine learning, and I mean, with the first results in the 2000s, more or less, when we have some seminal work like the HL algorithm. This is a quantum algorithm for calculating the inverse of a matrix. This is a problem that classically is not solvable by an efficient algorithm. So it requires exponential time. This algorithm, which is based on the quantum Fourier transform and all various trick of quantum algorithmic tricks that allows us to get some exponential speed up is actually very efficient if it could be implemented. Of course, this algorithm needs a completely fault-tolerant quantum computer, which is at the moment not available yet. So the use of this matrix inversion is in a quantum in the definition of the quantum support vector machine given by Lloyd, Moshemi, Rebentrost in 2013. This is based on the least square root, the least square formulation of the support vector machine. And essentially, it solves this system of linear equation by inverting this matrix efficiently. Of course, you need to embed all the classical data first into quantum states, and then all you have to do is to run the HHL algorithm and then get from this an estimate of the separator. All clear up to now? As I said, this is, oh, please write on the chat. I think I can see if there is any question, so I will just stop and answer to the question. So as I said, this quantum algorithm for machine learning, so this definition of the quantum support vector machine, are all algorithms that needs the full power of the quantum computer, and also the existence of a quantum random quantum random machine, so to you know encode the data, so are not realizable very easily. There is also a very strong limitation, which is that it has been proven that using machine learning algorithm with polynomial runtime, like the quantum support vector machine algorithm, it is not possible to achieve super polynomial advantage for supervised. This has been proven, and the reason is, I mean, intuitively, is that there are so many sampling error coming from the measurement process that actually the polynomial efficiency runtime is lost because of this you know, the need of getting the more sampling. So this is something that says that you know, if we just try to use quantum linear algebra subroutine, like for example the inversion, the algorithm for the matrix inversion, which are polynomial, which run in polynomial time. Well, we are not able to guarantee the efficiency of the quantum learning. And this is because of the, dependency on the approximation error of the approximation on the number of samples. So this is why actually at the moment, all the work in quantum machine learning has been done in yes, this is what I already said, has been done actually in a different way. So trying to use the quantum computer to enhance already known techniques in classical machine learning. And I will now present two approach, quantum kernel based approach, which are really the basic, the most well known in quantum machine learning. And these are based on the fact that on the idea of using a quantum device to implement the function class, okay, and then the optimization is done on a classical computer. Okay, so we just use the quantum device to compute the model, but in order to optimize the model, we use a classical computer. That's why I'm talking about these approaches as a quantum enhanced machine learning, okay, because there is still some classical algorithms and techniques that are used. So there are essentially two approaches. One is called the variational quantum circuit, and the other is called the quantum kernel estimator. So in the first case, we use variational, which means basically a quantum circuit with parameters. Then they are then trained and exactly like we do in support vector machine, and optimized classically. In the quantum kernel estimator approach, we just calculate the kernel by the kernel matrix by using a quantum computer. And then we use the classifier directly. And the advantage of this method is that they do not need a quantum random access machine, and also can be applied when data, of course, are provided from a classical computer. So let's go a little bit more in some more detail. So we call quantum neural network the approach based on a parameterized or variational quantum circuit. Okay, and these are based on training done via gradient-based optimization, classical gradient-based optimization. So don't be misled or confused by the name, because as we will see later, this quantum neural network have nothing to do with the deep classical deep neural network. Because they are just another form of quantum kernels, okay? And this will be clarified later. But so basically, the idea of using a quantum computer for computing a kernel, the kernel matrix, gives us an advantage with respect to using the classical support vector machine or supervised techniques, as long as the kernel is very difficult to simulate classically. So there we get really an advantage. And as an example of such a kernel, which is very difficult to compute classically, but can be computed by using a quantum circuit. So let's look at this quantum kernel defined via explicitly defining the feature map. The feature map is this unitary U phi, which is defined via this transformation, which is essentially a rotation, but is a very difficult one because it's a product on some rotations on each feature of the input data. Okay, and on this, then you take the sum of all the subset. So you can see here there is a combinatorial explosion. So this is why it's very difficult to calculate classically. And then this can be repeated actually several times to get at the end our kernel. Let's see a very simple example of application of this embedding, this feature map. Of course, the feature map embeds our classical data into the Hilbert space, which is the space of the quantum states in which we work. And then we just take the inner product in our Hilbert space and in our quantum space. So suppose that we have, for example, classical data, which are all the points in this line, 0 to pi. And then we want to classify in this way, okay? As you can see, we cannot do, we cannot define a linear separator here directly on the input data. So we have to map them into a higher dimensional Hilbert space. In this case, we map them into, so basically we map them into a state of a quantum qubit, okay? So we just need one qubit, and we can map each point of this line in the block sphere, okay? Which are all the states of one qubit. And we map that in this way. We take the U defined before. So for one qubit, for single points, real number, all we have to do is to rotate each number with around the Z axis, okay? And then we get this embedding. And you can see that by embedding this line into the block sphere, then we get a clear separation, which is this hyperplane between the red and the blue point. Of course, we can do that also by complicating the input. So, for example, now we can take as input data pairs of real numbers. And again, by applying the definition of kernel embedding that we gave before, then we get here. So first of all, the embedding would map each feature into xi, the component of x, and data pairs of data will be, I mean, we have only one subset of the set of the features, okay, because there are only two features. We map in this, product of pi minus x1 and pi minus x2. This is just an example, but it shows that what we get is something very,
excuse me?
Which is, yeah?
Can I ask a little technical thing?
Yes.
You go 2 slides back, please. So here I'm a little bit confused because you say the U matrix is unitary.
Mm-hmm.
Phi is real, I suppose.
So we have
the Z is complex.
So this is encoding essentially the real numbers, the input.
The Z is complex because it contains.
I is the complex number. So this exp. So it's this is a rotation, right? Because it's exp to I. And the sum of Z rotations, Z Pauli matrix. But sorry, this I is confusing. This is the imaginary number, and this I is the index over S, which is a subset of N, okay? X is a vector in the n-dimensional, is a vector of N reals, okay? Then you take all subset of these N reals, okay? And for each subset, you do the product of the Z, the Pauli matrix Z, over all these reals belonging to S, to the subset. And this is a real number, just encoding the vector associated to the vector is a real number by which you multiply this. It would be the angle in this case. Okay.
What is the relation between the Zi and Zx?
Because x is one only, so this is a vector which is 1 point, okay? Here, this is a generalization because you get here the different coordinate or features of these n-dimensional vectors, okay? So the I is to ranges over all the n coordinates of the vector x. Okay, so this would be Zi with I actually ranging over the set which is composed by X.
Yeah, I'm still a bit confused because the Z matrix contains complex number.
Which matrix? This one?
Zx.
Z is actually this matrix, okay? Is the
yes. If it contains a complex number,
yeah,
how can you be sure the matrix U is still unitary?
This is guaranteed to be unitary because it's actually the exponential of Pauli matrix or a sum of Pauli matrix, which is a rotation, and this unitary. So we can formally show this, but yeah, this is a unitary matrix because it's a rotation. Okay. I mean, it's like if you take, it's just a more complex form of the rotation in the block sphere around Z, Y, and X, right? But you have to see in a n-dimensional Hilbert space. Well, actually 2 to n, if you have n qubit.
Hi, Alessandra. If you don't mind my ignorance on quantum computing things, could you explain what the block sphere is and how?
Yes. Sorry. Okay, you're right. So the block sphere is actually a 3-dimensional representation of all the states of 1 qubit. Okay, so 1 qubit is the state of 1 qubit is typically represented as a vector in the 2-dimensional complex space, right? So you have alpha 0 plus beta 1, okay? So you have the vector 1 and the vector 0, which are the basis vector of the Hilbert space. And then any linear combination, complex linear combination is a state of a qubit. Right, so it is. We can show that there is a 1-to-1 correspondence between each of these states and points on the block sphere, on this 3-dimensional unitary sphere. Okay, this is something that you can show. So basically, you can look at each point on the surface of this sphere as a state of 1 qubit. One of the infinite space states of a qubit. So what we are doing is to basically encode each point of this line, okay, which is a single point, a real number, into one state of 1 qubit, which corresponds to a point in this block sphere.
Okay, thank you.
Okay, shall I go on? I don't know if the unitary. Okay.
Thank you.
Okay, so this was just an example, okay, and how to define a quantum kernel in a way that is not classically computable, and therefore you might get an advantage. Now there are, as I said, two methods we can use a kernel. One is the quantum variational classification. What we do here is to apply this circuit, the one that I defined before. So you have the embedding, then you apply the U, the rotation, and then you apply several times this U, and then you get this very complex embedding into a quantum, into a Hilbert space. It could be many dimensions, very high dimensional Hilbert space. And then after that, after the embedding, we apply a so-called training circuit. So we add some parameters that then must be optimized. And at the moment, so after running this parametric variational circuit, we apply a binary measurement to the resulting state, which is this one, okay? And then, we repeat this measurement until we get an empirical distribution, okay? So this is a distribution, this says that is the probability, the empirical calculated probability of associating a Y to the input data X. Okay, now we can define a classifier in this way. Basically, the label associated to X is Y if the probability that we got is of Y is greater than the probability of getting minus Y. And the optimization of the parameters is obtained by a cost function. The cost function can be defined by, for example, the empirical risk, right? So how much is the average of this overall the X of the probability of having different labels from the one predicted by our distribution. So this is one way of defining a classifier, quantum classifier. But the other one is the quantum kernel estimation. So essentially, all we do is to define our embedding. So embed the classical data into our quantum state, and then calculate the kernel, the pairwise kernel in this Hilbert space. And there are various ways of, so basically, the use of a quantum computer is calculating this very complex kernel, and we can do that by using, for example, the swap test. Okay, this is a very simple circuit that allows us to estimate the inner product between two input data. Okay, of course, in this case, we have we have to compute the kernel between these two quantum states in the Hilbert space where they have been embedded. Okay, so contrary to the classical case where the phi is not explicitly is never explicitly calculated, here the phi is our quantum embedding, which is crucial to define our kernel, to calculate it via a quantum circuit. Okay. Now, of course, the two methods have advantages and limits. The advantage of one method are the limits of the other. So, for example, using a kernel the kernel estimates, then we are guaranteed that the optimal kernel always can be always found, of course. And while if we use the variational approach, then I mean, this is a training, so this is something empirical. As if you remember, I was talking about empirical distribution. And so this doesn't give any guarantee of optimality. And so this is a limit of the variational learning. The variational learning is much more efficient as a method with respect to the kernel, the calculation of a kernel, because they require at least, the M square calculation, where M is the kernel matrix. We have to compute each entry of the matrix, while in the variational approach, we run the algorithm in a time which is linear in the input data. Okay, so now let me draw some conclusion. So I see that there is something in the chat. How many extra qubits do you need to perform the? Okay. Let me go back. Here we need for each pair of states, we need an ancilla qubit, right? Because this is used then to measure and calculate by measuring, by calculating the probability of getting 0 here. Then, I mean, if you do some calculation, you will see that this probability has this expression, and from this you can estimate the inner product between C1 and C2. So for each pair, you need actually an ancilla qubit. Does this answer your question? Okay. Okay. Then now we have quantum models with variational learning that, as I told you before, are very similar to neural networks, right? If you look at this circuit, looks like a neural network, a classical neural network with layers, okay? But actually, this has nothing to do with the neural networks because the layers here are not really layers, because they are multiplication of unitaries, which is, after all, one unitary, okay? So the difference with the quantum between what are called quantum neural networks and the real deep neural networks is that there is no deepness, so to say, in the quantum neural networks, because the training in the deep neural network involves non-linear functions that are not present in our variational approach, in what we call a quantum neural network, okay? So they are essentially intrinsically linear models. More formally, they both the quantum kernel and the quantum neural network, the two approach, the quantum kernel estimation and the quantum neural network variational circuit can be reconducted to this form, which is the a general form of a linear model, okay, where the phi are the feature functions, and theta j are the parameters, okay, the weights, the weight, what we call weight, weight in the initial definition, okay, and after all, this is nothing else than an inner product, right, between theta and phi of x, okay. So it is in the space of in the feature space, basically, okay, of the input. Also, the quantum neural network are linear model because I mean the only difference is that instead of the explicit inner product here, we have to calculate the trace. So if you go back to the the circuit that I showed you below. What we do with the variational approach, we just start from 0, then we apply the embedding, and then we apply the variational or parametric circuit, okay? And then at the end, we measure, so we apply an observable. So we have to basically calculate this corresponds, this measurement, to calculate the trace of the density matrix times the observable. Okay, and the trace is actually nothing else than an inner product. So this is also a linear model, and also V theta can be expressed. The various V theta that we iterate can be expressed as a product of unitaries, and the construction, therefore, of the layer-wise architecture does not exist because it effectively collapses into a single operation. So I hope this is clear that when we talk about quantum neural network, we talk about a linear model, and therefore these are nothing to do with the deep neural network, classical deep neural network. And this is actually one of the open problem, that quantum neural network are not able to perform deep learning. Okay, because in deep learning, we need to implement some activation functions, so-called activation function, going from one layer to another, and these are highly nonlinear, and there is no way to introduce them into a quantum neural network. So this is still characterized a truly deep model in the quantum domain is still an open problem. I think I'm taking too much time, but I hope you will still listen to these other problems here. What about quantum? Quantum reservoir computer is an interesting subject, but I don't know much about it. I'm sorry, so I cannot talk about that. I wouldn't know. So let me, before letting Massimiliano to talk about some solution to problem 1 and 2, let me, present this problem. So I have told you what a quantum kernel is, how we can implement it, but I mean, there are serious problems to implement this in practice, right? First of all, they very much choosing, the best quantum kernel depends very much on the data set, on the given data set. And in order to, so it sounds difficult how to practice. Oh, yes, if you refer to the implement quantum kernels, there are several problems. And one is that, for example, if we don't, exploit somehow or use some knowledge of the given data set, it can be not easy to define the best quantum kernel for our data, right? And then there are some solutions. There are some papers that have already, introduced some solution to this problem, like, for example, a paper by Liu Arunachalam and Temme, who exploits the group structure in the data. And from this group structure, they can define a kernel, which is classically difficult to compute. And this is a kernel that is defined by reducing the problem of classification, for example, to the calculation of the discrete log, which is something that where you can get a quantum speed up. And you can also try to optimize, once you have the kernel for your data, optimize it by using kernel alignment, okay? But there is also another problem. The other problem is that if you define very complex and complicated kernel, this can be so expressive. Of course, the larger is the Hilbert space, and the more complex it is. And of course, you may think that more likely it is to get an advantage. This is not true, because extremely large reproducing kernel Hilbert space, or large space for our kernel, quantum kernel, may lead to have a very small eigenvalue, so that you know we have potentially vanishing values for our kernel, so that it can be basically our kernel could be useless. Okay, some solution to this have been already proposed, and this is, for example, working on the inductive bias of the kernel, like trying to work on the so try to reduce the expressive power of kernels, for example, using projected kernel or via reduced density matrices. So somehow this is back to the first question: how complex should be the Hilbert space? Well, if you take too expressive, too much complex Hilbert space, too high dimensional, then you have this problem that your kernel could be useless, essentially, because the values are so small that you will need a lot of samples to be able to separate them. And also another solution is that to introduce some hyperparameters like the bandwidth, which is an hyperparameter introduced in classical machine learning, and this could be done also. This is the work by Scheidulin and Wild, where they introduce a quantum bandwidth. But I think I took too much time. I would like, if possible, if you're still willing to, to show a solution that we have studied for problem 1 and 2 for defining optimal kernels. And for this, I would like to ask Massimiliano, who is the main, the one who has worked more on this solution, to talk about it. If I still, can we take some more 10 minutes from you? I know that it's already.
Yes, as long as we give permission to those who have to leave, I think it's quite perfect that Massimiliano presents to us his part.
Yeah, sorry, I've taken too much time.
Okay, so Alessandra, can I share?
Yeah, stop share.
Okay, I promise I will be brief, hopefully. Can you see me? You can't,
Yes,
right?
We can see you.
Okay, perfect. Okay, thank you very much. With this very quick presentation, we want to give some ideas of how you can construct a quantum kernel for your specific problem. And in particular, we have discussed that this quantum kernel is implemented with a feature map, which is a parametric quantum transformation, a parametric unitary that depends on your data X, and depend also on the structure that you want to impose to this unitary. So the generators, the polymatrices that you want to include in your transformation. The problem is that clearly we have to have some criteria that allows us to choose the structure of this feature map and of this kernel, because if we choose a kernel that can really capture the data, the relation between the data, we will have a strong classifier. While otherwise, if we choose a kernel that cannot catch the relation between the data, the classifier won't work. And so without any prior information on your data set, you struggle to impose a structure on this quantum kernel. And we were thinking and still are of a solution for that. And in our analysis, we started from the characteristic that we want in a quantum kernel. The first one is that we want the quantum kernel to be non-classically simulable, because if we can run the problem on a classical computer, it makes no sense to, of course, to run it on a quantum computer. And in order to ensure this property, we have to look at the structure of this parametric quantum unitary. And usually this unitary is made of several smaller basic unitaries multiplied together. All of these are in the form exponential of -c, an angle that depends on the data and is Hermitian matrix. And all this sequence of Hermitian matrices that creates this unitary are used to define an object that is a dynamical Lie algebra, the algebra of the transformation we can perform with our unitaries. And if this dynamical Lie algebra has a dimensionality that is exponential in the number of qubits, it will be hard to simulate classically. It's not easy to check this property practically because there is no closed formula, but we can somehow approximate it if we just try to calculate the dimensionality up to a certain threshold. And after this threshold, we just say the unitary is hard to simulate. The second property that we want is that the quantum kernel must be not too much expressible. This is because very expressible unitaries presents unfavorable statistical properties, such as we spread the data all over the Hilbert space and the inner product will be very small. So we will try to have a quantum kernel that is not too much expressible. There is a problem, and the problem is that we can correlate the dimensionality of the dynamical Lie algebra to the expressibility somehow. So if we have an exponentially sized dynamical Lie algebra, we will probably have a very expressible unitary, and we will need a way to balance these two things. So we should have somehow a compromise. This compromise can be solved using expressibility control techniques. And for example, we can introduce a bandwidth. A bandwidth is like a preprocessing coefficient, which we use to multiply. We multiply all our rotational angle that depends on our data x for this coefficient that in between 0 and 1, and this will limit the angle of the rotation. It means that we can possibly use a very expressible unitary that exploit all the direction of this exponentially sized Hilbert space, which is very hard to handle. But since we can make only very limited rotation, we still have quite a small surface. We can control all the surface of this Hilbert space. And we have different techniques of expressibility control. And the third property we have to satisfy is the kernel compatibility, which means very briefly that we can design a quantum kernel and try it on our data set and hope everything works perfectly. But we have no guarantee that it will work, because each kernel can capture the relation between the data of a certain data set. So it means that every data set will have a different structure, and we cannot design a kernel that works for every possible structure. Each one must be picked and carefully designed. There is no general rule that allows us to carefully design the kernel, but we have some criteria that tells us if the kernel adapts empirically to our data. And one of these techniques is the kernel target alignment or the task model alignment. Now with this ingredient, we want to construct a quantum kernel. And we want that possibly an automatic procedure that chooses all the components I showed you before. And we want that this optimization technique to be quite fast. Otherwise, we cannot really run it. And the ingredients for building this kind of approach is having a model to describe a quantum kernel, one or more criteria that we can use to evaluate if the proposed quantum kernel is useful or not. And we need an optimization technique that can adaptively modify the quantum kernel in order to reach a sequence of solutions that are better and better. And hopefully the last one will be satisfactory to use. How we can model really this unitary? We can model this parametric quantum unitary as a sequence of operation. Each operation is described by the generator, which are the polymatrix that we want for our operation, the qubits on which this operation acts, the feature that parameterized the rotation, so our data, and an optional bandwidth that can act as an expressibility control. We have clearly a sequence of operation, since if we only consider one operation, the feature map will be too simple. And at the end, we have to perform a measurement that can be a measurement in the computational basis of the system, or can be something different. We can have different criteria to evaluate the kernel. These criteria can be such as the target kernel alignment, a criteria that evaluates if we satisfy the kernel compatibility, so the third criteria I've said you. But we can have also different criteria to evaluate our kernel with respect to the dimensionality of the Lie algebra of the unitary, which tells something about the first criteria I have shown you, the classical simulability, and so on. And in general, we would like to guide our optimization technique by optimizing a cost function that depends on many different criteria. So we want to define a cost function that depends on, for example, the criteria that calculates the rank of the dynamical Lie algebra, and also the target kernel alignment. And we want to consider all these aspects I have shown you before. And after that, we can, after we have defined this cost function, we just need to optimize this cost function, and the solution of this optimization process will be a quantum kernel that adapts to our problem and can be used in a useful way. Clearly, this kind of optimization is not efficient, will be non-convex, will be highly dimensional, and you can really exploit many different techniques. Each will have different characteristics. We have tried a lot of them to see how they relate to each other. For example, we have tried to optimize this cost function using Bayesian optimization that is particularly useful for evaluating very costly cost function, which is the case for our optimization task. But this Bayesian optimization technique usually struggle with high dimensional problems, and our problem is really high dimensional. We can recover positive solution if we try different variants of this Bayesian optimization. But since we have no time to dive in each technique, I can just show you the one that we have tried and why we have decided to try them. And after Bayesian optimization, we have proposed genetic algorithm, and these are very important because they can explore a really wide area of possible solutions, but still they are very expensive to run. but this is, was a possible choice. And furthermore, we have tried some artificial intelligence scheme, such as the one that depends on reinforcement learning procedure. So you just set up a sort of game in which you try to define a set of action that leads you to the correct solution. And finally, we have tried, the most trivial one, which is the greedy optimization technique that just tries each possible operation for each step of this optimization, pick the best one, and go on. We have some preliminary result about that, even though we are still developing this algorithm. In particular, we have tried these techniques with several real-world datasets. This particular dataset we have tried are somehow limited because we have no evidence that we can solve this algorithm with quantum kernel more effectively than with classical kernels. Still, we can have an idea if our optimization technique works. And the other limitation is that the number of features have been reduced to a number of 5, which is quite a little number, because we had a very not a powerful enough computer to simulate everything. Even with this limitation, we can prove that our optimization technique can improve the performance of this quantum kernel by up to an improvement of 60% compared to the randomly generated kernel, which are valid kernel for such small data sets. And what we still need to prove is that this approach really scales well than random kernels and scales well with respect to all the quantum kernel that we know in the literature. And finally, the purpose of our work was to try to define automatically a quantum circuit that can be used as a quantum kernel. And to do that, one of the possibility you can exploit is through combinatorial optimization following these very cheap numerical properties. Thank you very much. I hope it's...
Thank you very much, Massimiliano.
Yeah.
We have a big applause for you.
Thank you very much.
And maybe since we don't have too much time, maybe if there is one final question, either from the audience or online. There are a couple.
Okay, so in view of the time running out, just a quick kind of anecdotal question, perhaps. What is the role of Richard Feynman in quantum computing?
Sorry, what is the rule?
What is the role of Richard Feynman in quantum computing?
Ah, okay. Richard Feynman was actually the one who invented, we can say, because he said that, I mean, he is known for, quantum mechanics, and he said is known to, have this idea that, given that it's so hard to simulate quantum systems, so why don't we use quantum mechanics to simulate them? And from this, apparently, all the ideas about quantum computing came about. Is this the question? Did I answer?
Thank you. There's one last question.
Okay, thank you very much. I would just want to ask one little question. When you were defining your kernel, I was surprised, like you started defining the space, the data, and then the function from the data to the Hilbert space, which was you called the large Hilbert space. But my concern was, like, how did you construct this Hilbert space? Did you just, because there's infinite, there's a lot of Hilbert space, so how did you choose that? Which Hilbert are you going to choose?
Okay, that's
product also, is it going to be compatible with the, because there's also a lot of inner products you can choose. So which one is going to be, to make sense? Okay, thanks.
Okay. So the Hilbert space is defined essentially when you define the embedding. Okay, so you have a set of classical data, and you have to choose. I mean, it's really random, or you let some information, or maybe the data guide you. But you have to decide. For example, well, I associate to each data. To each data point, 1 qubit or maybe 2 qubit. And depending on that, then you construct the Hilbert space, which would be the dimension would be given by the number of qubit that we will use to, encode the classical data. So when then you define the embedding, that can be any unitaries or complex function, then the inner product of the Hilbert space that you have defined in this way will be exactly your kernel. So basically, the Hilbert space is the feature space that classically is not defined. It's given implicitly because classically the kernel is defined on the classical data, on the input data, on the training data, as in a way that the kernel matrix is a positive semi-definite as this property, the Mercer property. Yeah. So basically, is the Hilbert space in the definition of the quantum kernel is essentially the feature space, infinite dimensional feature space, or infinite space that you use for defining your kernel.
Thank you very much, Alessandra, and also to Massimiliano for a very interesting colloquium. We hope to see you soon, maybe here in Stellenbosch.
Well, that would be great. Thank you, everybody, for listening to us. I hope that you enjoy. And please, if you have more questions or curiosity, feel free to write to me. I'm always very keen to answer.
Thank you very much.
Thank you very much. See you soon.